So we finally finished the first chapter, which introduced the TensorFlow concept as well as some tools available in TensorFlow. Okay, and now we are in a position to talk about the artificial neural networks. Okay, here, okay, really the key idea that inspires artificial neural networks is the brain architecture. Okay, because we want to create the intelligence, right? AI, we want to create artificial intelligence. Okay, it's very natural, okay, to look at our own brain, because supposedly human has intelligence, right? So human's intelligence comes from the brain, right? So it's natural to look at the architecture or the structure of the brain. Okay, so Alan actually gets inspired from the brain architecture. Okay, and but now, okay, I be very careful. Okay, at the beginning, okay, Alan gets inspiration from the brain architecture, as I said. But now, okay, it has gradually moved away. Okay, it's now very different from the biological brain. Okay, because it has been found that a couple of key differences. Okay, if the AI is set, okay, using different functions, different settings, then it's going to perform much better. Okay, originally AI was designed, trying to copy everything. I mean, we have known from the biological brain. Okay, but now it's very different. Okay, so AI are at the very core of deep learning. Okay, because deep learning is pretty much a subset of artificial neural networks. Okay, so these ALNs are versatile, powerful, and scalable. Okay, so this make the ALN very ideal to tackle large and highly complex machine learning tasks. Okay, for example, classifying billions of images. Okay, such as Google images. Okay, you in the image. Okay, in the Google image, you can do a search, and there's a tab you can click, right? That will help you to identify the images corresponds to your search keywords, right? Okay, so that's what is accomplished by the deep learning. Okay, and powering speech recognition services. Okay, such as Apple Siri. Okay, behind Apple Siri. Okay, it's a deep learning engine. Okay, that does the job. Okay, and it can recommend the best videos that you can watch. Okay, for example, in YouTube. Okay, you can again provide a few keywords, and YouTube will automatically recommend you the best video for you. Okay, and also you can even learn how to play to beat the world champion at certain games, as complex as a Go. Okay, you can probably say that Go is by far the most complex game. Okay, that we have. Okay, but the DeepMind AlphaGo, okay, has no problem. Okay, beating human. Okay, the professional champion. Okay, I think the AlphaGo. Okay, now they have AlphaZero, which is said to be even more powerful. okay, than AlphaGo, okay. The AlphaZero is trained by the reinforcement learning. I'm not sure if we can cover reinforcement learning this semester, but I will try, okay. Well, so you can see all these tasks, okay, they are complex and difficult to accomplish, but the deep learning can accomplish them all, okay. So we are really at the stage of where we can say that we are at a high peak of artificial intelligence, okay. So now, I mean, a little bit of the history of artificial neural networks. Okay, this history actually, okay, also you can also consider that as a little bit of history of artificial intelligence. Okay, so the ALM or AI, okay, can be traced back to, it was first introduced back in 1943. Think about that. Okay, 1943 is like 70 years ago, right? Okay, it's of course it's not like a couple centuries ago, no, but it's still like a very, very long time ago, right? Okay, by the neurophysiologist, okay, this Warren McCulloch and the mathematician Walter Pitt, okay, so the ALM was actually introduced by a neurophysiologist and a mathematician, okay. Be very careful, okay. In 1943, okay, there's no Department of Computer Science, okay. Now, right now, like the computer science department, okay, no matter which school you are looking at, okay, the history, okay, the oldest one probably is about like 50 to 60 years old. That's already considered to be like probably the oldest one, okay, in the world, okay. But this one is like more than 70 years ago, right? So at that time, there's really no computer scientists out there, okay. So this is like back at that time, people want to find, they want to study like the source of the intelligence, and they came out with this idea. Okay, they presented a simplified computational model of how biological neurons might work together in animal brains to perform complex computations using propositional logic. Okay, at that time, okay, they really use the animal to do experiments. Okay, they use animal. They try to do some stimulation to the animal, and they kill the animal like immediately. Okay, and try to see what's the status of the neuron, okay, in the brain, okay, to study the brain architecture, okay, at that time, okay, because at that time there is no remote sensing, there's no, a lot of the technology was not available at that time, okay, so this type of study is kind of a very broad, okay, because they kill a lot of animals, but of course at the end they found some very important concepts. Okay, so early success of ALN, until 1960s, okay, led to the widespread belief that we would soon be conversing with truly intelligent machines. Okay, so about 1960s, okay, everybody think from the early success of ALN, okay, people start finding we do some, not very complex tasks, but they found that, okay, the simple ALN can be used to solve some, it's not very complex, but it's non-trivial, let me put it this way, non-trivial tasks, okay? So it's at least it's very promising, it shows promises that we can develop like a true intelligence by using the ANN architecture, okay, in the 1960s, okay, but it was a failure, okay, at that time. Okay, so that's actually the emergence of the AI, okay, the first emergence of AI, okay, artificial intelligence, okay, first emergence, okay. There were a lot of like scientists, okay, who spend like a lot of time, okay, doing this type of stuff, okay. They later, like, of course, a lot of them, they received like a lot of awards, such as Turing Awards, like, you know Turing Awards, right? I think I explained what Turing Awards. Like when Turing Award was first like created, the first few recipients, okay, actually like if you look at like recipients of Turing Awards, okay, you can see like of course the majority of the recipients, okay, are doing two types of research. The first type of research is artificial intelligence, okay. The second type of research is doing like theoretical computer science research. Okay, well, theoretical computer science research, I mean, because this is very theoretical, so if you have any finding, it's groundbreaking. Okay, it's a very important. It's not a surprise for them to win like a Turing Award. Okay, but like you can see a lot of recipients, early recipients. They have like they lay the foundation ANN, okay, in the early stage, okay. So so that a lot of them later became like a very important, very famous, became famous professors at MIT, at Stanford, at Carnegie Mellon. Okay, these few institutions, I mean, are still well known. Okay, even nowadays, right? Everybody knows. Okay, they are like top institutions like, in the world. Okay, so, but unfortunately, it turned out to be a giant failure. Okay, but in the early 1980s, okay, there was a revival interest in ANN. Okay, as new network architectures were invented and better training techniques were developed. Okay, so from the early 1980s to like early 1990s. Okay, so there's a second surge of artificial intelligence. Okay, so again, a lot of people like think like it's going to be like another 10, 20 years that like you are going to see like a robot like who can think and act just like a human. Okay, at that time, but unfortunately, okay, the second surge of the AI or ANN failed again. Okay, why? Because okay, around 1990s, okay, there are many powerful machine learning algorithms, such as SVM, were developed. Okay, and they found that okay, by using those simple, well, much simpler, like machine learning algorithms, okay, they can produce like the performance like much better than what they can obtain from the artificial neural networks. Okay, why is that? Well, in this class, I told you guys like machine learning is like a prerequisite. But I know that many of you really didn't take that course. Okay, but let me put it this way. Okay, the biggest issue is in terms of like there are a few reasons. Okay, the first reason is because the size of the data. okay, back in the 1990s, okay, the data size is considerably much smaller than what we have nowadays, okay? Okay, nowadays, if you are talking about like data size, okay, you can use a lot. There are a lot of sensors surrounding us, right? So we have like, we have like well, smartphones, right? We have like surveillance cameras, okay? We have a lot of pervasive equipment that continuously collecting data from everybody, every second, every minute, right? Okay, so we get a lot of data now, okay, but the situation is not like this, okay, back to 1990s, okay? So data size is considerably much smaller, okay? So when the data size is small, okay, you will find that the traditional machine learning algorithm, okay, is very easily outperformed, okay? It's going to outperform like ANN, okay? So that's the first issue. The second issue is that, okay, in the early 1990s, okay, apparently we don't have GPU, right? We don't have GPU. We don't have a lot of computing powers, okay? And if you want to create the ANN, a big and complex ANN, okay, when you need to train a big and deep ANN, okay. Oh, by the way, okay, it is known that deeper ANN, okay, can process a much complex task than wider and shallower ANN. Okay, so when you talk about ANN, the depth is normally more important than the width. Okay, but when you have a deeper ANN, the training become more difficult. It requires more computation power. Okay, but back to 1990s. Okay, the computation power is not that much. Okay, but nowadays it's different. Okay, first we have we have much more computation power. Okay, a mobile device this size is much stronger than a server back to 1990s. Okay. Secondly, now we have GPU, right? We have NVIDIA GPU cards, okay, which allow us to do parallel computing in large scale, right? So all these are not available in the 1990s. Okay, so this is another big difference. So unfortunately, this second search failed again. Okay, so I'm sorry, this one. Okay, failed again. Okay, so finally, we are now witness yet another wave of interest in ANN. Okay, so today, okay, as I said, we are at the high peak of deep learning or artificial intelligence, or ANN, okay, whatever you call it. Okay, this is really the third wave. The third wave. Okay, does this wave going to be successful, or is going to be another failure? Well, some people may think it's going to fail again. Okay, but okay, there are some reasons that allowed us to be a little bit more optimistic. Okay, than at least compared with the previous two waves. Okay, first, as I said, okay, now we have a huge quantity of data available to train neural networks. Okay, so ANN frequently outperform other machine learning techniques on large and complex problems. Okay, such as the problems I just mentioned as an example. Okay, Siri, video searching, like image searching, and as well as like the AlphaGo, all those examples. Okay, so also tremendous increase in computing power. Okay, since 1990s, makes it possible to train large neural networks in a reasonable amount of time. Okay, this was not available in 1990s. This is in part due to Moore's law. Okay, you know Moore's law, right? Every couple of years, okay, the computing power doubled. Okay, so this Moore's law, okay, allowed us to have a much stronger, much powerful computing devices, like at a cheap price. Okay, but also thanks to the gaming industry, which has produced powerful GPU cards by the millions. Okay, well, of course, like NVIDIA's GPU card originally designed not for the AI, of course, we know that, right? It was designed for gaming industry, right? Because gaming industry was like perhaps like one of the most important money-making industries in computer field. So like NVIDIA spent a lot of like energy or time to produce the GPU cards, but it was like found that GPU card can be used for like parallel computing, okay, by accident. So it becomes like interesting, like we can make use of that to train a large, deeper ANN, okay, with a reasonable amount of time. Okay. And also there are other reasons as well. For example, the training algorithm have been improved. Okay. To be very honest, okay, there's really no significant modifications. Okay. The principle, the basic principle stays the same. The basic principle stays the same. Okay. But there are some small tweaks that has been found, okay, in recent years, like in recent 20 years. So these relatives, although these are the relative small tweaks, okay, but they have huge positive impact, okay. I would talk about some of those things, okay, such as like remember previously I talked about like optimizers. I talked about like auto diff, right? Like reverse mode auto diff, right? I mean those concepts, okay, they were developed like in recent 20 years, okay. So even though conceptually, okay, these are just small tweaks. I mean because like the principle stays the same, okay. The basic principle really doesn't change much. But because of those small tweaks, okay, it actually bring like a huge performance boost, okay, and also some theoretical limitations of ANN have turned out to be benign, okay, in practice, okay. For example, many people thought ANN training algorithms were doomed because they were likely to get stuck in local optima, okay. But it turns out that this is rather rare in practice, okay? So remember we talked about like local minima, remember? Okay, when we talk about like gradient descent, remember? Okay, so gradient descent could end up like stacking at the local minima, okay? But it turns out that it's really not very common. It doesn't really happen that common. Okay, so it's really not that big issue. Okay, and ANN seems to have entered a virtuous circle of funding and progress. Okay, so because ANN is very successful, okay, so now people start doing investment on the research of ANN research. Okay, and this investment, okay, will bring some innovations, and those innovations will become a push force to some very useful applications, which in turn attract more funding. So this become like a kind of like a positive, like a cycle, okay, for this research field, okay. So amazing products based on ALM regularly make a headline news, okay, which pulls more and more attention and funding to them, okay. So resulting more and more progress and even more amazing products. So this is like a kind of like a positive impact, like impact, okay. Like one brings out another. So these signs, okay, tell us like it's promising. This third wave of ALM is very promising, okay, at least. Okay, so after this little bit of history, okay, let's first look at the very beginning, the root of the ALM, which is like a biological neuron. What does it look like? Okay, it looks like something like this. You can see we have a cell. Okay, the neuron is a strange looking cell. Okay. It has like this is cell nucleus, okay, and the cell actually is a very long, okay, okay. It's an unusual looking cell, okay, mostly found in animals' cerebral cortex, okay, composed of a cell body containing the nucleus and most of the cell complex component. Many branching extensions called dendrites, okay, plus one very long extension called axon, okay. So we have like this is dendrites, okay, dendrites, then it's dendrites, okay, dendrites, and this is very long. This long branch is called axon, okay. So you can see it has many branches. Okay. Each branch is connected to another neuron. Okay, each branch is connected to another neuron. Okay, so and this cell, okay, the axon's length can be just a few times longer than the cell body, or up to tens of thousands of times longer. Okay. If you're talking about like the neurons in our spine, okay, there are neurons, neuron cells in our spine, okay. The neuron cells in our spine can be as long as like a more than 1 meter long, okay. So it could be very long, okay. So near its extremity of this axon splits off into many branches called pterodendria. Okay, here. This pterodendria. Okay, so this pterodendria, okay, and at the tip of these branches are minuscule structures called synaptic terminals, or just synapses. Okay, this one. The synaptic terminals or synapses, just synaptics. Okay, and okay. Which are connected to the dendrites, okay, of other neurons, as I said, okay. So biological neurons receive short electrical impulses, or we call signals, from other neurons, okay, through these synapses, okay. When a neuron receives a sufficient number of signals from other neurons within a few milliseconds, it fires its own signal. Okay, so if you receive like inputs, okay, or signals, whatever you call it, okay, input from some other neurons, okay, if the input total is greater than a threshold, it will fire its own like input and output that. It will fire its own output and send it to other neurons that it connects to. Okay? So individual biological neurons seem to behave a rather simple way, okay? But they are organized in a vast network of billions of neurons. Each neuron typically connected to thousands of our neurons. Okay, look at here, thousands of our neurons. Okay, so in our current ANN, technique, okay, we normally do not create N of such size. Okay, even now, for now. Okay, so you can say that, okay, our brain is a very advanced neural network, has a very advanced neural network. Okay, much advanced than the NVIDIA 10880 type, it's expensive one, right? You guys, I told you guys to get like some hardware, and some of you complain that it's expensive. But each one of you carry something that's much more complex than that GPU card. So, so highly complex computations can be performed by a vast network of fairly simple neurons, much like a complex anthill, okay, can emerge from the combined efforts of simple ants. Okay, each ant can only do very simple tasks, but if you have like thousands of of ants, okay, they can build an anthill not only very big but also complex in structure. Okay, so so actually just this thing, okay, there's like an ant colony algorithm out there that allowed us to use like simple rules to deal with like complex problem. Okay, I don't know, some of you have heard about this type of research. Okay, if you don't know, just do a search out ant colony, ANTCOLONY, colony, ant colony. Okay, this is like one of the simple important research directions, kind of like belonging to artificial intelligence as well. Okay, by the way. So architecture of biological neural networks, okay, is called BNN. It's still the subject of active research because people are still trying to find which part of the brain is in charge of what. Okay, like if we can tweak some part of the brain to maybe to heal a patient, something like that. For example, if a person has Alzheimer, okay, is that a way that we can somehow fix that issue, something like that, those issues, okay? It's still a very active research topics, okay? But some parts of the brain have been mapped, and it seems that neurons are often organized in consecutive layers, okay, like this. Well, it doesn't look very easy to understand, but you can kind of see because here is we are trying to see. It's kind of like we are see. If you try to rotate 90 degrees, okay. This is the input, okay. From the input, okay, you can see there are some layers like shape, right? So this is we can say there are multiple layers in a biological neural network. Okay, this picture is actually obtained from the human cortex. Okay, in your brain, it looks something like this. Okay. So these two researchers, as I said earlier, okay, McCollum and Pitts, okay, they proposed a very simple model of biological neuron, okay, which later became known as an artificial neuron. Okay, it has one or more binary, okay, either on or off input and one binary output. Okay, the artificial neuron simply activate its output when more than a certain number of its input are active. Okay, it's very simple. Okay, so this one, of course, is not ReLU. Okay, it's even simpler than the ReLU. Okay, so McCulloch and Pitts showed that even used like such a simplified model, it is possible to build a network of artificial neurons that computes any logical proposition you want. Okay, I will show you an example in just a few minutes. Okay, so for example, here, okay, just we show like a few ANNs that perform various logical computations, assuming that a neuron is activated when at least 2 of its inputs are active. Okay, here. Okay, if you want to do C equal to A, just because A is branching into 2 inputs and connected to C directly. So if A is active, C must be active, right? If A is not active, C is not active. So C equal to A. Any question? Easy, right? Okay, here we assume, okay, C is active if 2 inputs are active. 2 or more inputs are active. Okay, so here, okay, see, if you want to compute C equal to A and B, then if A is active, B is active, of course, because C has like C received like 2 signals from A and B, so C will be active, right? But if one of them is active or both of them are not active, then C doesn't have enough signal to be active, right? So that's C equal to A and B very easily, right? Okay, so this one, okay, is C equal to A or B, okay? You can see if A is active or B is active, or even when A and B both are active, C will be active, right? But if both A and B are not active, C will not be active, which is exactly the case of C equal to A or B, right? The last one, okay, if you want to do something a little more complex, okay, this is like a C equal to A and not B, okay, so it's like A, you have it's branching into 2 inputs, and the B is connect to inverse, okay, and 2 C, okay, so you can see, okay, if A is active, okay, then if A is active, B is active, okay, then because A is active and B is active, then not B is going to be inactive, right? Okay, so you get two positive inputs, but you get 1 negative input, which cancel out 1 input, cancel out 1 positive input. So you don't have enough positive input to file C, right? Okay, but if A is active, B is inactive, then you have 3 positive inputs, right? So which will file C, okay? That's the only possibility. The other cases, you don't have enough like a positive input to activate C. Okay, so this is like some example to show you. Okay, any question for that? So this, you can see like by using this simplified like a neuron, okay, we can actually use that to simulate the computation of like a complex proposition. Okay, easily actually, easily. Okay, of course, like if you have a proposition, okay, you may end up, you may need to have more than one. This is only we have like 1 layer. Well, 2 layers if you count like the top one and the bottom one. Okay, but if you have a little more complex position, you may have more than 2 layers. But still, you can easily create like neural networks that compute exactly the complex proposition that I give you. Okay, it's not an issue. Okay. So this is explanation. I don't think I need to go through that. Okay, it's very easy. Okay. So so now we are in the position to talk about like the first like real like meaningful like a unit in the neural network. Okay, it's called perceptron. Perceptron. It's one of the simplest AI architectures. Okay, which is invented in 1950 by Frank Rosenblatt. Okay, this is like one of the very famous computer scientist who has made like a significant contribution to the AI. Okay, in the early stage. Okay, so it is based on slightly different artificial neuron. Okay, called a linear threshold unit. Okay, so we talk about like a ReLU, right? Okay, so ReLU is a rectified linear unit, right? But this one is a linear threshold unit. Okay, it's abbreviated as LTU. Okay, so what's like this? Okay, it's like input and output are now numbers. Okay, instead of binary on-off value. So this is not like the model like McCulloch and Pitts proposed. Okay, previously. Okay, so this is a little bit more complex. Okay, each input connection is associated with a weight. Okay, in some sense, it's a little bit it's more close to the ReLU that we have talked about. Okay, okay, so LTU computes a weighted sum of its input. Okay, so Z equal to W1 x1 plus W2 x2 blah 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 plus Wn xn, so equal to WT, the transpose of the weight. Okay, vector inner product x. Okay, they apply a step function to that sum and outputs the result. Okay, so a couple of difference. First, it does not have compared with the ReLU, it doesn't have the bias, right? It doesn't have bias. Second, okay, this one, like LTU, uses step function, okay, which is different from the ReLU, which use like a rectify function, right? So a little bit different, okay. So we normally denote the LTU like this, okay. We sum up all these inputs, okay. So we put a summation symbol here, and then we put the step function symbol here, okay, and the output will be this one. Okay, I think this is very easy to understand, right? Okay, so we can actually, okay, so most common step function that we can use, okay, in perceptron. The first one is like this. Okay, if Z is smaller than 0, it's 0. If Z is greater or equal to 0, it's 1. It's very simple step function. Okay, it's either 0 or 1. Okay, if the weighted sum is smaller than 0, it's 0. The input, the weighted sum is greater or equal to 0, is 1. Or we can use the sign function. Okay, in other words, if the Z is smaller than 0, it's negative 1. If Z is 0, it's 0. If Z is greater than 0, it's plus 1. Okay, either one of these two. Okay, so there are these two choices of step function. Okay, so this is not really like a, because when we talk about step function, what you may have in mind is like a flow function or ceiling function, right? You map to like an integer, okay? But no, it's not just like any integer. It's it's only mapped to either 0 or 1, or it's mapped to negative 0, negative 1, 0, or 1. That's it. Very simple case, okay, here. So single LTU can be used for simple linear binary classification, okay? It computes a linear combination of the inputs. And if the result exceeds a threshold, it outputs the positive class, or else outputs the negative class. Okay, because it's either, assuming we are using Heaviside, okay, Heaviside step function, you can see clearly that it has two different classes, either 0 or 1. Okay, for different output, we assume it's going to represent different class. Okay, so it's going to binary, simple linear binary classification. Binary classification means like there are only two classes out there. Okay, so it's either positive class or negative class. Okay, so it's kind of like a logistic regression classifier or linear SVM. Okay, if you don't know what these two algorithms are, okay,